Swayam Prabha. Digital India. Educated India.
Thank you, Raj. Good morning, ladies and gentlemen. This PSE Asia is our Asian version of Process System Engineering Conference. And it's held every 2 years in different parts of Asia. So 2 years from now, we will see you in Malaysia. Okay, the team has been set, PSE, Incubating Sustainability for Industrial Revolution 4.0. Okay, you notice that we put August. We haven't really decided the dates. I'm checking with delegates from all over Asia on the right dates. I've asked a few people, including Japanese, Korean, a few. So please feel free to talk to us, your preferred date. And our main organizer is Institutional Engineer Malaysia, and that's supported by those organizations. In terms of Malaysia, you probably knows that our capital city is Kuala Lumpur. This is the map of Malaysia. We are West Malaysia, and there's a Borneo Island, which is the East Malaysia. If you plan for a holiday trips, no other necessary COVID test, nothing. Just come in anytime, anywhere, from any parts of the world. We are well connected. We haven't really decided where our location for the conference. You notice that I've been talking to people, and the regular PSE participants says, Kuala Lumpur is a bit boring. Can we go elsewhere? Yeah, we are now thinking north of Malaysia, either Langkawi or Penang. Those are the places that we are thinking, looking forward. But we are looking forward to hear from you. Tell us if you prefer Kuala Lumpur. And come and tell us if you do not like Kuala Lumpur. Then we are now surveying hotels in different parts of Malaysia. I asked a few people, some of the regular senior PSE scholars have told us that Kuala Lumpur is a bit boring every time it's Kuala Lumpur. Okay, now we are looking at the north. So this is one of the potential location, Langkawi. Okay, many people know this as a famous tourist spots. If you plan to also take some site tour, so these are some places that you should go. Another option is Penang, the picture on the right-hand side. We also survey Malacca. This is the historical city of Malaysia, more than 600 years old. The other two are East Malaysia. If you plan for holidays, Sabah and Sarawak are good options after or pre or post conference. Okay, the most important attraction for Malaysia is food. We are known for Malaysia. Truly Asia. Whatever food you look for, Chinese, Indian, you want to duplicate Madras food in Malaysia, you can find it a lot. So Chinese, Malay, and Indian foods, these are the most popular one, and many others. Okay, so we look forward your participation in 2024 August and PSE Asia 2024. This will be the 11th PSE Asia, if I remember correctly. All right, that's all for the slide. I will show you the montage. This is a very short montage, then we can go on to the presentation. All right, let me just run it again. Thank you. Stay in touch, and please get a copy of the brochure for PAC 2024. I hope it's still available in the registration counter. See you in 2 years' time. Thanks.
Colleagues, we then continue with the rest of the session. The first presentation for this session is the Beacon lecture, which is going to be presented by Professor Zofia Luxko, and the title is Hydrogen for Climate and Energy Targets in Europe. I'll read the bio for Professor Luxko. Prof. Zofia Luxko studied applied mathematics at the Technical University of Łódź and philosophy at the University of Łódź in Poland. In 1996, she received her PhD degree on her thesis, A Practical Approach to Recipe Improvement and Optimization in the Batch Processing Industry at the Eindhoven University of Technology in the Netherlands. Since 1995, Zofia has been working at the Faculty of Technology, Policy and Management at Delft University of Technology in the Netherlands. She's a full professor there in the Energy and the Industry Group. Until the academic year, 2017-2018, she was the director of the SEPAM, which is SEPAM, Systems Engineering, Policy Analysis and Management, now called COSEM Master Program at TPM. Her research concentrates on a wide range of problems in the way complex socio-economic systems are functioning today and can be reshaped for the sustainable future. The questions she works on concern investigation of supporting technology and emerging institutions for the transition towards sustainable energy systems. Shaping smart grids requiring additional flexibility from the users in cooperation with dispatchable power plants, storage and interconnections forms a main pillar in her research. Zofia is a steering board member for PowerWeb, an interfaculty research program on smart grids at TU Delft. Welcome, Professor Zofia.
I am here. Good morning. I can't see if I am visible or not on your screen.
You are very visible. And
do you see my presentation also? So, yes.
Yeah, there it is. We can see it now, maybe in the presentation mode. You can go to the presentation.
Yeah, I how to come to this from the beginning. And now, can you see it?
Now, that's it, yeah. Okay, over
it's
to you.
Okay. So, good morning to everybody. My name is Zofia Luxko. I am professor of smart energy systems at the Technical University of Delft in the Netherlands, and I am at the Faculty of Technology, Policy and Management. Today, I would like to share with you the ideas how hydrogen can be used for the climate and energy targets in Europe, maybe to inspire you or so that you can compare what is the situation in Europe and in Asia. And my presentation is divided as follows. I will start with some history, European package Fit for 55, to go further to the Repower EU and Hydrogen Accelerator to show to you the European hydrogen policy. Some remarks about the last State of the Union in the European parliaments, to go finally to modeling of integrated wind hydrogen system. And this brings me to the working on green hydrogen in the Netherlands, in the country I am coming from. And I will conclude with key challenges for the research and PhD community. Let me start then with some history. Exactly, more than a year ago, the European Green Deal initiative called Fit for 55 was presented. And why Fit for 55? Because the European Union decided would like to be first climate neutral continent in the world by 2050. And to reach this, the goal was formulated of achieving the CO2 emission reduction by 55% by 2030. So on the short notice, so the 55 shortly. It means also that some measures are published and proposed to achieve the CO2 emission. And one of the important one was related to the role of hydrogen in our economical system. So in the Fit for 55, we see a clear announcement regarding deployment of hydrogen markets, because they are not really in place now, and the regulation in incentivizing of uptake of the hydrogen. And the European Commission will play an important role. And why we are talking about the hydrogen in the energy transition and for the realization of the climate goals? Maybe that is well known to you, but I would like to stress again that the most important role that hydrogen can play in our future economy is because it enables the renewable energy system. It is an enabler of a fully renewable energy system. And why? Because it enables the large-scale renewables integration and power generation. It is easy to distribute and to transport, and it can act as a buffer to increase the system resilience. Besides these important roles in the energy system, hydrogen can be also used for the decarbonization of the end users. And it is in decarbonization of the transportation and many means of transportation, by also in the decarbonization of the industrial energy usage, decarbonization of the built environment for heated power in the built environment, as a renewable feedstock in the industry, especially maybe interesting for the PSE community. So in the Fit for 55 package, some targets were defined that 10 million of hydrogen should be produced in 2030, of produced or important by, we would like to have in 8 years, 10 million tons renewable hydrogen, green hydrogen, so produced without any emissions in the Netherlands, and to be used in different areas, and especially for the industrial production and for the transportation. And maybe interesting to mention, one of the clear goals was to design the fueling station network in European continent, so that every 150 kilometers the fueling station for hydrogen will be available, and also in all cities at least one hydrogen station is available. By having the fueling station and hydrogen backbone for transporting hydrogen is not sufficient. So European Commission, and that was a year ago, proposed a framework for decarbonization of gas markets. So it is about the developing of markets, promoting hydrogen, and reduce the methane emission. So I will highly recommend it to look further to the link provided, interested document. By what is mentioned there, that the hydrogen market should be established, that they make a distinction between before 2030 and later on to reach these goals of 2050 being first climate neutral continent. And a dedicated infrastructure should be also developed, and having the technical infrastructure as said, also the institutional context make possible trading with third countries should be developed. And a new governance structure is developed. The European network of network operators for hydrogen is established to operate hydrogen infrastructure, cross-border coordination, and interconnector network construction. so that also the special technical rules on national and European level can be developed. That was exactly a year ago. By then, the situation in the world was changed. And as we know, in February, Russia attacked Ukraine. And that was for European Commission and the point to decide to become totally independent of Russian fuels. And also to speed up the energy transition, to speed up the process of becoming climate neutral, so that we can provide more affordable, secure, and sustainable energy system to all. That is also the process where we have actually the most strong and most clear way to go to the rapid, to clean energy transition at the whole European continent. So to become totally independent of the Russian gas and gas fuels, it means that we need to have an of usage of other energy carriers. And there is a very important place for the hydrogen again. Repower EU, thus the joint program was announced in March and fully formulated and presented to the member states in May this year, together with the Hydrogen Accelerator, a program to develop infrastructure, strong facilities and ports for the import of hydrogen, and the replace demand for the Russian gas, so that we have additional 10 million tons of green hydrogen already in 2030, above those we proposed in the Fit for 55 package. And if you look further on this table, that is maybe a lot of details, but in the middle, you see that the Hydrogen Accelerator would like to boost production and import to 20 million tons in year 2030. So a doubling of the goals presented in the Fit for 55 package. And it means also a lot of R&D challenges. That is nice that European Commission proposed this, by how to get there. And then you see in the Repower EU, again, in my right corner, it is about the diversification of the energy sources. As said, the hydrogen plays important role, accelerating the energy transition and also working on the saving energy, and also the smart investments. By how to get there, as I said, a lot of challenges for R&D. So to decide, and you need to think not about one country, by 27 member states in the European Union, to decide where is the best place to generate the green hydrogen, and giving maybe the existing infrastructure for electricity, for the gas transport, by also taking into account the demand and future demand. As said, the demand will come from many sectors. How do we get the hydrogen from production to the consumption? So not only to how to generate, but how to transport hydrogen. How do we store hydrogen? And what are the places? Do we do this at the national level as we did until now for the gas storage? Or maybe we will have the European gas storage facility. Is there any competition with offshore CO2 storage, for example? What way of monitoring transport usage and storage are in place and how they should be improved? And maybe most important question, how do we reach these 2030 goals in a way that we can upscale the system easily to reach the 2050 goals easily, and as set 2050 to become first climate neutral continent, and many others. And in September this year, in the State Union, the President of the European Commission, Ursula von der Leyen, presented in her speech a very, very important message for research and development and our energy transition. Hydrogen will be a game changer for Europe. What does it mean? Actually, it accelerates the role of hydrogen even more than in the past documents. What is stressed by Ursula von der Leyen, that we need to move for hydrogen from the niche market to the mass markets. We will double our targets as presented by the REPower EU to have 10 million of hydrogen produced in Europe and 10 million of hydrogen imported by 2030. So we need to create the institutional context for a market for hydrogen. How we will do this? By creation a new European hydrogen bank, so that the guarantee for purchase of hydrogen can be given. So maybe the national governments, even European Union, will be responsible for purchase of hydrogen, and a lot of money will be spent for the huge hydrogen market and establishing need. What we needed, that is, I will say, integrated electricity hydrogen energy system, and maybe even more integrated energy hydrogen system. For this presentation, I will a little bit concentrating more on the integrated wind and hydrogen system, because they are the first steps which are taken into consideration. So that by developing the massive wind parks we are now developing in Europe, we can integrate the hydrogen developments in the energy system. What is needed? Actually, it is clear: hydrogen certification system for blending for the green, blue, and turquoise hydrogen, and maybe also for the years in between gray hydrogen. If you are not familiar with the colors of hydrogen, the green hydrogen is the carbon neutral, turquoise is produced without CO2 production, and blue, it is with CCS storage or CCU utilization. What is also important, that is to develop new hydrogen pipeline infrastructure. And in the Netherlands, we especially look at the North Sea with all countries around the North Sea. But it's not only necessary to develop this infrastructure technically and maybe reuse, but also to decide about the ownership, how to regulate, how provide the permits. So this is actually a challenge to have the coherent institutional and technical design. And the coherent and technical and institutional design applies not only for the transport of hydrogen, but also for all other parts in the chain: production, storage, and maybe further. And what is important, that the infrastructure will have the open access, and so we think about the private-public ownership. And offshore wind hydrogen development should be on the location which are most cost efficient. So not thinking about system efficiency, but I will say the cost efficiency is the most important. So minimization of system cost is the issue. The infrastructure should be connected for the European hydrogen backbone on the mainland, which is now on the development. Also, a roadmap for offshore hydrogen storage should be developed, and also with the wish to have the open access, publicly regulated offshore hydrogen storage with public-private ownership. And also thinking and deciding the level of the strategic reserves for hydrogen is new for us. Countries has only the strategic gas reserve on the national level. By how to decide this for hydrogen is a big challenge. To decide should be done on the European or national level. And as said, in the hydrogen infrastructures, when we decide how to build this, the existing pipeline infrastructure should be taken into account. And if our wish is to be to import 10 million tons of hydrogen, green hydrogen in 2030, we need to decide, should we use the existing infrastructure connecting us with Tunisia, Morocco, from Asia, also from Saudi Arabia, and how to connect this to the pipeline infrastructure at the European continent. And to decide how to design this infrastructure, and in connection with the wind parks, which should be developed on the short notice in the Mediterranean region, for Netherlands important the North Sea part, but also Ostsee part, the decision should be taken regarding the means of transportation of energy. And it is clear that the gas infrastructure in Europe can be reused for hydrogen, but the question is which parts of the gas infrastructure should be reused. And when we build and new wind parks, should we go for the transportation of energy by usage of the electricity cables, high voltage cables, or we will go to usage of the gas infrastructure, which is also available in the North Sea and other locations, as mentioned, Mediterranean region and the Ostsee. And what I would like to stress when transporting the energy, gas pipe capacity is more or less 10 times bigger than capacity of the electricity cable, with the gas pipes, which are now in average in our system. We can transport 10 to 20 gigawatt, and capacity of the electricity cable is 1 to 2 gigawatts. And we can also estimate that the gas transport is, it means also the hydrogen transport through the gas pipelines is factor 10 cheaper than the electricity transport. And this brings me to the research which we do in my group, Energy and Industry Group, to support the energy transition to develop the integrated energy hydrogen system. We developed the comprehensive modeling approach for the integrated electricity hydrogen system for the North Sea, and we will extend this to the bigger parts of Europe. And what does it mean, the comprehensive modeling approach? We try not only to model the technology, but also the important actors and their behavior in the whole supply chain. So starting with the producing companies, building also the wind parks at the North Sea to provide electricity, but also companies, and there are different companies responsible for transport and distribution. Maybe also they will be responsible for storage of hydrogen. The institutional context should be still defined, and we also take into account in our model, as said, the technical part when we model the wind farms and platforms, compression station, cables, pipelines, landing points at the continent, and the demand for hydrogen. To do this, we use the principle of agent-based modeling because it makes possible, as said, to model the actors and the technical parts. We would like to see how different choices will influence the levelized cost of electricity and levelized cost of hydrogen at the landing points, and maybe the existing one or the new one. And what are the choices we would like to investigate? That is where to produce where to build the wind park. So what are the appropriate location to put the wind parks on the North Sea? How to transport the energy by electricity cables or by the pipelines? And what are the connection with the landing points? To do this, a lot of inputs for the model is needed, and electricity demand should be defined, the expected hydrogen demand, and expected the technology development. And that is actually not the preliminary and first stage model. So we continue by just give you an impression how we do this. You can see the input we used for the model, for the agent-based model. We looked at the average wind speed of the North Sea and created the distribution of the wind speed. That is the first part of the graph. We use information regarding the water depth. We use also in our models information regarding the existing pipeline infrastructure. That is the third figure in the bottom line. And also you see there the dots showing us the landing points, but it is only for the gas infrastructure. If you look at the gas infrastructure, it is also important to stress that this infrastructure which is not owned by one operator, by many operators, independent operators. So as said, thinking about the coherent institutional and technical design is a sine qua non condition, because you need to get these actors, different actors, with the ideas you have in mind. We also used the electricity interconnectors and landing points in the infrastructure. We exclude some economic zone in our assignment for the decision of the wind park production, and the exclusive economic zones that are used for the transport of ships, by also ecologically restricted areas used for military purposes. They are excluded from our calculation. we proposed looking to the national scenarios, some hydrogen electricity demand over years per country. We also introduced some technology learning curves by also look at the storage possibility in the North Sea. In the North Sea, we have salt covers location in the North Sea, but also in the main lines, and they can be used for the storage of hydrogen. But also depleted gas fields are the candidates for the storage. And as said, the traffic on the North Sea was taken into account. This finally also bring us in the decision how the hydrogen production should be integrated with the wind parks and with the electricity production. We distinguish three possibilities to produce hydrogen onshore and offshore centrally and in the wind turbine, so in the decentralized way. And why this type of distinguish we met to decide now what is the economically feasible construction of the integrated wind hydrogen system. When you have the onshore production, we are going from the EC to the DC, through the AC-DC conversion and again EC-DC conversion. So you have the 5 conversion steps from the wind parks to the final electrolyzer to transport them further through the backbone to the demand. By then 5 conversion steps, which are costly. If you look at the hydrogen production in the offshore park and on the platform, you have only 3 conversion steps, and this will also minimize the system cost. By finally, and that is new technology possible, that in the hydrogen production can be done in the wind turbine. It minimizes the conversion steps only for 1 conversion. And it means there is no central platform and the system costs are much less. And we can, by the offshore case, in the turbine, have only the gas treatment in compression step on the platform. And the outcome of the comprehensive system modeling was the map of the North Sea. I concentrate here only on the map of the Netherlands with the color part of the North Sea. And what was clear, that we have a clear distinction between the ways how the hydrogen production should be integrated with the electricity production. In the yellow area that is close to the shore, so plus minus 75 kilometers from the shore, my video, yeah, it is coming, yeah. So 75 kilometers from the shore, only electricity production should take place. When we go further, that is the light blue area, more than 100 kilometers from shore, the wind hydrogen production take place. So the hydrogen production will be integrated with the wind turbines, and the dark blue and gray area, that is not the area in between, when we can, depending on the situation, divide of the electricity and hydrogen production. What is clear, that further from shore, the hydrogen production is cheaper than electricity production when you look at the landing points and the mainland. So we look at the levelized cost of the hydrogen and electricity. And when we are further from shore, more than 100 kilometers, the hydrogen production is cheaper. And floating wind turbines are also a very interesting development to make the further cost reduction, because you don't need to that they are flexible. You don't need to invest the rigid structure to connect them with the bottom of the sea. And as said, the in-turbine hydrogen production minimize overall cost and losses. So that is the first step, how to decide what type of the production should be in place. To sum up this, you can see here that the wind hydrogen production at sea is cheaper if we go further than the 100 kilometers from shore. We can use existing and fewer landing points, and also less surface area on land is needed for the production of the hydrogen. It means that the pipelines should be, which are already available, repurposed. Some addition should be added, and we can also repurpose platforms and gas fields. It makes the transition faster, with less environmental impact and with fewer materials. The modeling study was done for the whole North Sea, so not only for the Netherlands, but by a similar study also for Belgium, UK, and Scandinavian country. By this brings me to the national challenge, how to decide the roadmap for green hydrogen in the Netherlands. And also at the national level, the green hydrogen is seen as a driving force for the energy transition. And our Dutch government awarded a big funding of millions, many millions of euros to support the emergence of a hydrogen economy. In the National Growth Fund, which is mainly intended to stimulate the economic development of the country, called the Groenvermogen, and meaning the green power of greening the country. A lot of money is reserved for research and development. And that is about the innovation, upscaling of the developments, and converting and rebuilding the infrastructure and production facility, by also about the retraining and training the people to make this energy transition. So we ask ourselves, what does it mean, the Repower EU to the Netherlands? As said, in the Repower, we are talking about 10 million ton hydrogen production and 10 million ton for import 2030. If translated to the Netherlands, we think about 1 million ton green hydrogen in 2030, and the same amount of import, 1 million ton in a few years.
Us?
And
Can you hear us?
Yes, can I continue?
Yes, maybe if we could be drawing to a close now. I'm looking at time. We're not doing
Okay,
well.
Then now the program is defined, and now modeling effort should be done to answer the question how to do this. Maybe then we can look at the program of the national program, which is divided in the 7 themes I would like to share with you. And the themes are regarding the production of hydrogen, that is the first work package. And the second one, which is presented in red, transport of storage hydrogen. And the next are related for the usage of hydrogen in a different sector in different ways. By the transport, the storage is so important because it is actually about the designing the whole integrated energy hydrogen system. It is about the infrastructure issues, how the infrastructure can be reused, about safety, about the upscaling of the infrastructure and storage system, and connected the roadmap development for the whole European development, and thinking about the infrastructure in relation to the offshore hydrogen production and system optimization and large-scale hydrogen storage. And I mentioned this comprehensive system modeling, the agent-based model. We work on it. At this moment, we start in my group a new research project, which is continuation of the first study, and a research project called the Hydrogen Value Chain Deployment and Agenda for Emerging Hydrogen Economy. With many PhDs, we will work here in the first part on designing the system. In the second part, that is the light green, about the robust design. If the conceptual design is done, then in the robust design and later on in the robust optimization, we will take into the account many uncertainties, and we will decide how to cope this by using robust optimization to come to the robust solution. And in the gray part of the project, from design the action, will concentrate on designing the institutional context, the rules, regulation, coordination mechanism, and all this parts together should bring us to the hydrogen value chain deployment. In the vertical part of the project, you see that we'll use also serious game to involve the important actors to play with us in understand some choices better and seeing how their choices influence the emergence of the supply chain. Here you see some studies which are related to the robust optimization. You see 3 big companies in the Netherlands from the processor industry, refinery. We look at the possibilities for them, firstly in the deterministic case, how to change the production ways by using hydrogen or electrification or CCS. And later on, we change the standard and deterministic optimization, which was done with the mixed integer linear programming, to the robust optimization by identifying uncertainty and going to the robust solution. And we look how to get to the efficient robust optimization methods. And that is just an example. But let me go to the key challenges and then I will close the presentation. The key challenges and important at the national and European level, by actually I will say also at the global level, that is developing the economically viable offshore wind hydrogen production, in the first instance offshore wind hydrogen production. By later on you can also think about the offshore solar hydrogen production and even onshore. infrastructure and storage, so designing the system and once the package of the grondvermogen, punten, infrastructure and storing, by also aligning key stakeholders, that is government at different level, local, national, European, aligning stakeholders and industry.
Yeah, no, it's becoming very difficult for us to keep up with the time. It's also rude to the next presenters. It's just gone way beyond the prescribed time, about 12 minutes now. So I think with that, we'll communicate if you have questions to Prof. Lusko, because it's a very good presentation. You are at liberty to email her, and I'll also explain to her why we had to stop, and then ask the right questions.